Okay. All right. Today we're going to start on a slight, well, it's not really a new topic. We are still in partial differential equation. We are still in finite difference method. Just that we're going to move on from solving 1D finite difference method to 2D finite difference method. All right. Before I get on to today's class, just a quick recap on what we have covered so far with regards to PDE. When we talk about PDE, the first thing we talk about is the classification. Okay, so for a for second order PDE, you can classify them into elliptic, parabolic, and hyperbolic. So those are based on the coefficients in front of your second order derivative. Then we looked at basically how we can solve parabolic PDE. So for parabolic PDE, we basically looked at the heat equation where you have dq dt is equals to T squared Q dx square with thermal diffusivity. So this is, I believe, one of the questions that you have to answer in your computer lab. All right. Just that in your computer lab, this second order derivative was written in terms of spherical coordinates, but effectively it is still a parabolic PDE. It is still a heat equation. So for this parabolic PDE, we looked at three methods to solve it. You have your FTCS scheme, you have your BTCS or your implicit FTCS, and of course you have the Crank-Nicholson scheme. Okay, so for each of these schemes, you need to know how to derive it. You need to know how it is implemented. Although realistically, we won't be asking you to do the hand calculation, but you need to understand the concept of how it is being done. Okay, and you also need to do the von Neumann stability analysis for each of these methods that you see here. Okay, so the method is general, but when you apply it to different PDE, you get different algorithm, you get different scheme. So for each of these scheme, the analysis of the von Neumann stability criteria is going to be slightly different. Okay, so the idea here is to understand how to perform it rather than memorizing the steps. Then we looked at basically hyperbolic PDE, although technically we didn't look at hyperbolic PDE. We looked at the 1D heat equation, but the 1D heat equation behaves, or the solution behaves like a hyperbolic PDE. So in this case, we have looked at FTCS, which we found to be unconditionally unstable. So unconditionally unstable also means it is always unstable. Okay. So from here, we looked at how we can solve this unconditionally unstable issue. Effectively, there are actually more than one method, but the one that we looked at in class is the Lax method. So you need to know how the Lax method actually overcomes the stability issue of FTCS scheme. And we looked at a different way to analyze the stability, which is based on the Taylor series substitution. Okay. So in addition to von Neumann stability analysis, you looked at Taylor series substitution. So when we substituted the Taylor series expansion into our Lax method, we found that, before that, when we substituted into the FTCS scheme, we found that the resulting equation that we have contains a numerical diffusion term. So that numerical diffusion term basically has a what we call a negative diffusivity, and that negative diffusivity is the reason why we get instability in our numerical algorithm. Okay, so for today we're going to move on from one-dimensional to two-dimensional PDE. Whatever we have covered here is one-dimensional in space. Okay, so although your Q or your unknown is a function of also time, in terms of the space dimension, it is one dimension because it is only a function of X. Today we're going to look at something slightly different. We want to look at what we call the 2D heat equation. So for the 2D heat equation, it is still a parabolic PDE. In this case, if you look at your equation here, on the left-hand side, you have D temperature, D time is equals to D. In this case, D is still your thermal diffusivity. And on the right-hand side, you have d squared T dx squared plus d squared T dy squared. Okay, so if you contrast this to your one-dimensional PDE or one-dimensional heat equation, you will have something like this. Okay, so in two dimension, you will have a second spatial derivative term given by d squared T dy squared. So T or capital T here is our temperature. T as usual represents time. X and Y are the two Cartesian coordinates. Okay, so if you guys recall when we did one-dimensional PDE, as what I've written here, we write, for example, let's say we talk about the advection equation here. Because q here is a function of x and t, when we write it in terms of finite difference method, we call it qj level n. So j represents the space point, n represents the time point. Okay, so what happens now when we have a two-dimensional PDE? So t here, or capital T, is your unknown variable. And because we're going to retain what we have before, we will have tj and we will have time level n. So n will still refer to the time level. Right now, you have two space coordinate. You have your y and you have your x. So right now, we are going to say that j represents the x coordinate. So how do you represent the y coordinate? We will introduce another index called k. Okay, so when you solve a 2D PDE, okay, make sure that you write it as t subscript j and k and superscript n. When you solve a one-dimensional PDE, make sure it is j and superscript n. A lot of students during exam, they will like to write tjn or qjn or even qjk like this, and they refer to k as the time derivative. I will minus marks for this because I specifically said in class, subscripts are reserved for space dimension. Okay, so if this is the two-dimensional heat equation, what we want to cover is the Crank-Nicolson scheme, although you are also expected to know how to solve it using FTCS or even BTCS scheme. Okay, but as you will see, they are all very similar. If you use Crank-Nicolson, you can understand Crank-Nicolson, you should be able to understand BTCS. FTCS is in fact more straightforward because everything would have been known from the current step to solve one unknown from for the next step. Okay, so if this is the PDE that you want to solve, do you guys remember the Crank-Nicolson scheme? Are you guys there? What is the Crank-Nicolson scheme? How do you write the left-hand side for the Crank-Nicolson scheme?
Sir, the left-hand side should be in the center scheme, right?
Sorry?
The left-hand side is using the center scheme, right?
The left-hand side will be the central difference scheme, but with Crank-Nicolson scheme, we take this time derivative at the midpoint between n and n plus 1. So time level n is our current point, time level n plus 1 is the next point. When we take this time derivative, we take it at the midpoint, n plus half. Okay, so if you take it at the midpoint, your central difference scheme for the left-hand side will be, sorry, I'm using the wrong one. Tjk n plus 1 minus tjk time level n divided by delta t. So this will look like your typical forward difference scheme, but because it's Crank-Nicolson, it is taken at the midpoint. This is effectively a second order scheme or central difference scheme. Okay, and on the right hand side, we take the average of the spatial derivative at n plus 1 and time level n. Because if the time derivative is taken at the midpoint, the space derivative has to be taken at the midpoint as well. So in this case, it is just a simple average between this and this. Okay, if you don't understand what I'm talking about, you need to go back to the lecture on parabolic PDE and refer back to how Crank-Nicolson scheme work. All right. So in our case, if we take the average, we can take out the factor 2, in which case you have d over 2, and then you get this very lengthy expression. So we'll do it for d squared t dx squared first. You have your tj plus 1, k minus 2, tjk over delta x squared. And you can see that here only the j is changed because the derivative is taken with respect to x. And we have said that this represents the x and this represents the y. Okay, so when you take a derivative with respect to x, you're taking it with respect to a constant y, which is why the index for k does not change. So this will be the one that is evaluated at n plus 1. And because we're taking the average, you will still have the similar expression, but this time, this entire thing is evaluated at time level n. Okay, if you stop right here, then you're not doing it correctly because you're ignoring the y derivative. So you need to do the same thing. You need to take the central difference scheme for the y derivative, but you need to take it at the midpoint, in which case right now you have tjk plus 1 minus 2tjk plus tjk minus 1. Okay, so these are at time level n plus 1. And you can see that because the derivative is taken with respect to y, the index k is the one that changes, while the index j remains at our current point, which is point j. And here you will have your tjk plus 1, tjk plus tjk minus 1. Okay, so this is your Crank-Nicholson scheme to solve a two-dimensional heat equation. Any questions?
No, sir.
All right. Today's lecture, I'm just going to outline the concept. So make sure you guys understand the concept. Tomorrow's lecture, I'll guide you guys in terms of the implementation in MATLAB. Okay, because Lab 6, as you'll see, involve a two-dimensional PDE question. So the MATLAB part, I'm going to guide you tomorrow. So if this is your Crank-Nicholson scheme, as usual, all the unknowns are moved to the left-hand side, all the known values are moved to the right-hand side. So the same thing is going to be applied for 2D heat equation. N plus 1 are all the unknown values. We assume time level n will be known. So if you rearrange this equation, you should end up with something like this. So you can see on the left-hand side, you have all the n plus 1 terms, which are the unknowns that you want to solve for. And on the right-hand side, you have all the n terms, which are solutions at the current step. Okay, so our object, if you look at this equation, you have one equation that consists of three unknowns. Your three unknowns are tj plus 1, so it's actually 5 unknowns. Tj plus 1, tj minus 1, k plus 1, k minus 1, and jk at time level n plus 1. So this is an implicit scheme. You cannot solve it directly, which means to solve this equation, you will have to set up a system of linear equation or system matrix. So before moving on, look at this equation and we try to understand what this equation is trying to tell us. Because if you recall from one-dimensional PDE, in your one-dimensional PDE, when you solve for your FTCS scheme, for example, this is your x, this is your t. At this particular point, if you recall explicit FTCS scheme, it takes contribution from these 3 points to find out what this is, correct? And then for this point, it takes the combination of three of these points to find out what this is. That is your explicit FTCS. For implicit FTCS, for implicit FTCS, if you want to find out what is this point here, or the 3 points in front at n plus 1, requires the knowledge of 1 point at the previous step. Okay, so in your Crank-Nicholson scheme here, what does this basically mean? If you look at what we have here, we have a two-dimensional PDE. Okay, so we have a two-dimensional grid point. In our one-dimensional problem, this is our x, this is our t. Okay, in a two-dimensional problem, it will be different. In a two-dimensional problem, you will have your x and you have your y. So if you want to draw the time scale as well, effectively, it will be something like you have your x, you have your y, and then the time scale would be the third axis that move forward. Okay, so this is how we are going to understand it. Again, if you look at what we have here, because of the way we solve finite difference method, we distribute a grid points. If you look at what we have in terms of the index here, first of all, we have a point jk. Okay, remember we have t, j, k, time level n. So j and k and n are basically our present point. If we say we are at our current point, we'll be at point j in terms of x, point k in terms of y, and time level n in terms of t. So if you look at this equation, there will always be a point jk, which is our current point. Okay, and then you have a j plus 1. Where is j plus 1? If we use the coordinate system of x and y like this, where is j plus 1? J plus 1 is actually 1 point to the right. correct? Because when we do our central difference scheme, we are taking j plus 1 and j minus 1. So j plus 1 term is basically the the point to the right of our current point jk. You have a j minus 1. So what is j minus 1? J minus 1 is a point to the left, okay? And on top of j, you will also have your k plus 1 and k minus 1. So if this is jk and k represents our y-axis here, then k plus 1 and k minus 1 would refer to the top and bottom of point jk. Okay, so effectively what we have is, in a two-dimensional distribution like this, you are going to distribute grid points across your x and y domain. Okay, in your one-dimensional problem before this, what you do is, when you solve your finite difference method, this is your x and this is your t. What you will normally do is you are going to discretize the grid points in terms of x, and then you're going to determine how many time level you need to move up to solve for all the time that you have. So effectively, you're actually distributing grid points like this. When you solve a two-dimensional problem, you have a two-dimensional spatial grid of x and y like this. So your x and y right now becomes a grid points or mesh grid that you see in my sketch over here. Okay, so this is y is your space, this is your k, this is x, which is your j, then your time level, which is b or t. So you're translating from a 1D problem to a 2D problem like this. So you can see as your t goes up, you have all this distribution of points. In your case here, if you have your x and y, if you increase the time level to solve for n plus 1, effectively you are distributing grid points, the same grid points, but right now you're distributing it at time level n plus 1. Okay, so you have to visualize this in a three-dimensional sense. Okay, so there's a sketch later that I'm going to show you, but for now, when you distribute your grid points in the x and y direction, what you see is you see that in your one Crank-Nicholson equation here, it will always involve 5 points. So what are those 5 points? Those 5 points are defined by these 5 points over here. Okay, it is your jk, which is your central point, your j plus 1k, j minus 1k, j at k plus 1, and j at k minus 1. So this collection of 5 points here is known as your 2D stencil for finite difference method. Okay, and when we apply our equation, every time we apply this equation, we always apply it at the center point. What do I mean when I say apply the equation? It's the same as when we were talking about one-dimensional equation. When I say set n equals to 0, set j equals to 1, meaning that we are applying it at n0, j equals to 1. So we're applying it at this point in order for us to find out what is going on at the same point at the next time step. Okay, so when I say collocate for 2D, it means that we are going to apply this stencil to the grid points that we have. So for example, if I say set it at n equals to 0, j equals to 1, and k equals to 1, it means that if this is j equals to 0, j equals to 1, k equals to 0, and k equals to 1, it means that when I apply it here, I'm applying my stencil at this point, so it will involve these 5 points here. That is your stencil. Okay, so for better representation, when you distribute your grid points, it will look something like this. Okay, so in your x and y, you will have your distribution of grid points. At time equals to 0, which is at t equals to 0 here, all the values are known from the initial condition. So when we solve it, we want to solve for the same grid points, but at a time level of delta t from the previous step. Okay, are there any questions so far? It is very important that you understand the concept behind these grid points, behind the stencil, and behind the 2D finite difference method. Okay, if you don't follow this, you will find it difficult. You'll find it difficult with the numbering, you find it difficult with the coding, and definitely you'll find it difficult with your final exam. Okay, so there's this question, does that mean we will need to have predefined values at all four corners? It means that if this is, let's say, X and Y, okay, let's say you're given a problem like this, and I'll give you an analogy to the problem that we have in one dimension. In one-dimensional problem, you need to have two boundary conditions, correct? For example, you need to have Q equals to 1, Q equals to 0, or you can have dq, dx is equals to 0. So your boundary conditions are basically the endpoints because it's a one-dimensional problem. In a two-dimensional problem, you need to have values at all the boundaries. So it's a matter of dimensionality because in one dimension, in a straight line, the boundaries are the endpoints, okay? In two-dimensional problem, the boundaries are the curve or the lines that bind the domain. So if this is a domain here, the four lines here that form the rectangle or the square would be your boundary. So for example, if you're going to discretize points, if you're going to discretize a grid points like this, okay, for you to be able to solve this problem as the heat equation subject to these grid points here, you will need to have the initial condition, okay, which is the value of t at any point xy but at time equals to 0. You need to have the initial condition. In addition to that, you need to know the values of all these grid points which are at the boundary. So not only the corner points, you need to know all the points that are at the boundary as well, because your boundary right now are basically the four lines here. So let's say we have this example here where this two-dimensional domain where the width of the square is of size 10. You're told that time ranges from 0 to 1 and the temperature distribution is described by this equation. Okay, so we'll assume that an initial condition is also given to us. So right now, if the problem says that the d is equals to 1, the delta x and delta y is equals to 2.5 each, and delta t is equals to 1, how can we solve this using, for example, the Crank-Nicholson scheme? Okay, so the first thing we need to do is we need to distribute grid points across our two-dimensional domain. So when we distribute our grid points, let's say we are using delta x is equals to 2.5. So for this, for length of 10, you will have 4 interval of 5 points. So the 5 points that you have are basically 1, 2, 3, 4, and 5 in x. And in y, you have the same thing. You have 1, 2, 3, 4, and 5. Okay, and then you're going to distribute these points across the domains that you have. So you have all these blue points along, as well as the black dots that you have, that you see over here. Okay, so right now you can see the one with the red triangle means that the values are known from the boundary condition, and that is true because everything that is on the boundary here, they are known from the boundary condition. For example, at the bottom boundary, all the temperatures at these points here, they are known and they are given by a value of 10. At the vertical boundaries, sorry, they are given by 0. At the vertical boundaries, you have 0 as well. And on the top horizontal boundary, you have a value of 10. So everything that you see with the red triangle, they are already known from the boundary condition. Okay, so if they're already known from the boundary condition, it means that the unknowns that you have, okay, the unknowns that you have are basically the points at the middle of the domain or at the center of the domain. And when you solve this problem for, if you solve this two-dimensional problem, what you're trying to solve for is for all the interior points, because all the exterior points would have been known but from the boundary condition. It's the same as a one-dimensional problem. When you distribute your grid points like this, anything that is already known from the boundary condition, you don't have to apply your point there, okay? Except if you have a Neumann boundary condition like this, but that you already know how to do it from that 5. But assuming that these are the boundary conditions that you have, when you move forward in time, all the values at the boundary is already known from the boundary condition, so you don't have to actually calculate for it. Okay, so the only unknowns are the ones at the interior. So the same thing applies for a two-dimensional problem. When we solve this, we only want to solve for the unknowns which are at the interior point. Okay, and as I've said before, if you're using the Kronecker scheme, you can see that it always involves this two-dimensional stencil. So what we want to do is we want to apply this equation, this entire equation here, which means to apply this stencil across the points that we have. So this is our stencil here. You want to collocate it at point JK, meaning that you're going to apply this stencil at each of the unknown points that we have. Okay. All right, so I'll hold the questions for now because I think I should explain the concept next before I open it up for question. Okay. All right. So first of all, if you look at the way I number the grid points here, I'm numbering them according to it's like a matrix system or it's like a grid point system. So I have the discretization in terms of J, I have the discretization in terms of K. So T10 corresponds to the value of T. If you have JK, it will correspond to the value of T10 when J equals to 1, K equals to 0. T20 corresponds to the point when J is equals to 2 and 0. So by that extension, we have this point here. Okay, we have this point where T11 represents J1 and K1. So this way, we actually numbering it based on the J and K point that we have. Okay. Now, it is important for you to note that when you set up an equation, like this, when you apply the stencil at one point, that one point will give you one equation. Okay, so when you want to solve your system matrix, you have to solve it in terms of the number of unknowns that you have. So in our case, in this particular example, how many unknowns do you have? The unknowns are, again, as I've said earlier, they're all the points at the middle of your domain. So you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so to make things easier, okay, we are going to renumber this into this convention. So we just say that the first point T11 or the first unknown point, we're going to call it T1. The second unknown point, we're going to call it T2. The third one, we're going to call it T3. And then you have T4, T5, T6, all the way to T9, corresponding to your 9 unknowns. Okay. For now, you may not see the application of this, but in tomorrow's lecture, when I show you how to implement this in MATLAB, you will better see why this thing is important. Okay. But for now, just accept it that in order for us to solve it in MATLAB, your matrix must be written. Okay, you guys know from your BTCS scheme, your matrix has to be written in terms of A times some unknown matrix equals to a right-hand side, correct? So this column vector T should be a column vector of all the unknown values. So you have these 9 unknown values, which means you should have T1, T2, all the way to T9, okay? So the matrix A should be the coefficient in front of these 9 unknowns here. All right. So this is why we have to renumber this from a grid point to a column vector numbering system like this. I've prepared this again to make it easy for me to sketch. So what we're going to do next, again, I have written everything because I don't want to spend the entire lecture writing things down, but you can just ignore the equation first. The first thing that we want to do is just like your one-dimensional problem, we want to apply the equation at the grid point that we have, okay? Because it's a 2D problem, you have to apply what we call the stencil. So the stencil, as I said earlier, involves the 5 points. So the first point that you want to apply is at J equals to 1 and K equals to 1, and you set N to be equals to 0. So when I say apply this stencil at J1 and K1, in the 2-dimensional grid that we have here, sorry, this should be Y. In the 2-dimensional grid, it means that we are going to put in that stencil involving that 5 points. And we know that the middle point is JK. So we want to put it at the point where J is equals to 1 and K equals to 1. So if this is the grid that we have before this, is this the same grid? Okay, this is probably, this is not the right grid. Okay, this one has actually 9 points, but I think, wait, is there 9 points? Sorry, that's not, there are 9 points. So, okay, this is the boundary. Let's not confuse it. And you have the 9 points in the middle, okay? So from here, if you want to apply it at J1, K1, you know that J1 and K1 is referring to this point over here. Okay, so when we apply our stencil to this point, it means that in your equation, in that Crank-Nicholson equation, you are going to involve this set of 5 points. Okay, so from this set of 5 points, all you have to do then is to sub in J equals to 1 and K equals to 1 to the index that you see over here. Okay, and of course we have set it to be n equals to 0. So when you do that, you will end up with an equation like this. So you have T11 minus D delta T over 2. Here you can see you have 211101, which are basically the 3 points here. And then you have 1, 2, 1, 1, and 0, 1. So there will be the 3 points in the vertical direction. Okay, and you can see based on the stencil that you see over here, this point and this point are basically known from your boundary condition. Okay, so if something is known from the boundary condition, you're going to move it to the right hand side. So in which case you can see where are the boundary conditions. These two are the boundary conditions. So 0, 1 and 1, 0 are the boundary conditions. So you know that this here and this here are the boundary conditions, which you can then move to the right hand side, like sorry, this one. Okay, this is at time level 1, this is at time level 0. So the one that we move to the right hand side is actually the one from the time level 1, because the values from there are from the boundary condition. So this equation will give you one equation, or this collocation will give you one equation in terms of 3 unknowns. Okay, so the 3 unknowns are basically your T11, okay, your center point. And if you just look at the stencil itself, if these two are your boundary conditions, then the remaining unknowns are your T11, T21, and T12. And effectively, they are the ones that I'm highlighting here: T11, T21, and T12. Okay, so this is also T11. So you can see when you apply one equation to that stencil, you get one equation in terms of 3 unknowns. Okay, if I ask you why did we start with J equals to 1 and K equals to 1, and we don't start with, for example, J equals to 0 and K equals to 0, you should know by now why we don't collocate it at this point. Okay, for example, if you put it at J equals to 0, where would be your stencil now? If you put it at J equals to 0, then your stencil would have been, sorry, so that's J0. Let's say J0, K0. So this is your J0, K0. So your stencil would have been something like this. Okay, and you can see that it involves 2 points that are beyond your solution domain. So that is why we don't collocate it at J equals to 0 and K equals to 0, which is the same reason why we don't do it with a central difference scheme for the 1D problem as well. Okay, is this clear?
Yes, sir.
Right. Okay, so this would be the first equation. You cannot solve it. One equation, 3 unknowns. The next thing, we're going to move on to the second point, J. Okay, so here we are done with K1, J1, K1. Next, we move on to the second point. So the second point would be J equals to 2 and K equals to 1. Okay, so when you do it for J equals to 2, K equals to 1, what do you have? You will have these 5 points as your stencil. So if you look at what you have, the 5 points would be your 1, 1, 2, 1, 3, 1. There'll be a J minus 1, J plus 1, J and J plus 1. And then you have 2, 2, 2, 1, and 2, 0. So that will be your K plus 1, K, and K minus 1. Okay. So again, if you sub in the index for J, K, and N into your Crank-Nicholson scheme, you will end up with this equation. And here, if you look at this grid index itself, you will know that there is only one boundary condition, which is your T20. Okay, so this is your boundary condition, and you can move this to the right hand side, and this becomes your equation 2. Okay, so this concept you're going to apply to all the 9 unknowns that you have, or these 9 collocation points that you have. So if this is J2, K1, then the next you will have to do it for J3, K1, which will involve this point. In this case, you again have 2 boundary conditions. Next, once you're done with j equals to 3 and k equals to 1, then you can go back to j equals to 1 and k equals to 2 to apply your stencil here. Okay, so effectively what you're doing is just similar to what you're doing for the Crank-Nicholson scheme in 1D or the BTCS scheme in 1D. Okay, just that instead of having just one line, you have a distribution of two-dimensional grid, and you have to apply your stencil or your equation at every single point that you want to find the unknown. Okay, so for example, when you do for J3K1, you get this equation. And then you move on to J1 and K2, you get another equation. And you're going to repeat this so that it covers all the 9 points that you have described. Okay. And if you do that correctly, you will find that you will end up having a system matrix that involve the 9 unknowns that you have. So you have your T11, T21, T31, all the way to T33. Okay. So it will be a matrix of 9 by 9 involving 9 unknowns given by the grid points that you have. And then you have your corresponding right-hand side. Okay, so doing this is tedious because you have to apply the stencil every time. There's actually a much easier way compared to what you have here. So when I say tedious, it means to write out every single equation like this. Okay, so there's actually a much easier way if you recognize what is going on with the Crank-Nicholson scheme. Okay, if you look at the Crank-Nicholson scheme, where is the scheme? Yeah. Okay, before I move on to that, do you guys have any questions? I feel like I've been talking for too long, so let me stop for a bit. Any questions? No? Okay, so if you guys look at the Crank-Nicholson scheme here, and again, this is only true because we are solving the heat equation, but you should be able to see the same trend or a similar trend if you solve any other PDE in the future. Okay, so from here you can see that in this equation or in your two-dimensional heat equation, you have your dt d time is equals to d squared t dx squared, and you have d squared t dy squared. Okay, so the spatial derivatives here actually give rise to the j plus 1, j and j minus 1, and it also gives rise to the k plus 1, k and k minus 1. And because of the Crank-Nicholson scheme, you have similar terms on the left-hand side and right-hand side. Just that one is evaluated at time level n, one is evaluated at time level n plus 1. Okay, so noting this and noting that this scheme here actually give rise to the 2D stencil because we're using central difference scheme. It gives rise to this 2D stencil. What we can do is we can rewrite this in a system matrix. So this is basically what I say. The expression that you see here in the left-hand side and the right-hand side, they are similar, just that they're evaluated at different time interval. One is at n plus 1, one is at time level n. Okay, so to make things simple, we can rewrite this scheme here in a system matrix or matrix format. And to do that, we basically say that the point tjk, we can call it a column vector T. Okay, so what is tjk? Tjk is the temperature T at all these points that we have. Because remember, it's J and K. So effectively, it's like the temperature of the grid that you have. So instead of calling it as a grid, we call it a column vector, which we will call T. Okay. Next, we are going to introduce a matrix L. Okay. So this matrix L, we are going to say that it comes from the partial derivative term of d square dx square plus d square dy square. Meaning that if you put a T here, it will be the second order derivative of this capital T, or the temperature. Okay, so we define L as this, which means that if this is this derivative or the differential operator, if we apply the central difference scheme, it will involve this term and this term, correct? Because the central difference scheme, okay, if I put a capital T, maybe that's clearer. The central difference scheme for this will give you this. The central difference scheme for this will give you this thing. So what I'm trying to say here is that here I am introducing a matrix L, okay? And this matrix L will take into account all the coefficients in front of the spatial derivative. Okay, if you don't see that now, that is fine. When I set it up, perhaps that will be clearer. But my point here is we replace the tjk as a column vector t, so that if this is n plus 1, this will just be n plus 1. Okay, and then we have our matrix L. We introduce matrix L because, first of all, L basically represents Laplacian, and we call this the Laplacian matrix. Why Laplacian matrix? Because this term here you have learned from ENG 2005, this is the Laplacian of t. Okay, anytime you take d square of a variable by dx squared plus the derivative in y and z, if it's 3D, you get what we call a Laplacian. Okay, so we call this the Laplacian matrix, and the Laplacian matrix will contain all the coefficients in front of our central difference scheme. Okay, and based on what we write here, we can write this scheme in terms of a system matrix, and our system matrix will look like this. First of all, you will have an identity matrix times your T. Okay, so this will correspond to the first term in our Kronecker-Nicholson scheme because we have called tjk as a column vector T. So this will be T at n plus 1. Okay, then we will have minus d delta T over 2, which is the coefficient in front of it. Is a coefficient in front of this. Okay, and then here you have the bracket of all your Laplacian term. Okay, this is your entire Laplacian term, which we are going to say it is going to be replaced by the Laplacian matrix. Okay, the Laplacian matrix, as I've said, contain all the coefficient in front of your unknown temperature T within the spatial derivative. So here you will have your Laplacian matrix times all the unknown T at time level n plus 1. Okay, and this will equal to the right-hand side. So the right-hand side, the first term is still your tjk. So we have an identity matrix times T at time level n, and then we have d delta T over 2 Laplacian matrix times T at time level n. Okay, so I here is basically an identity matrix. You guys know what an identity matrix is, right? Okay, it's basically a matrix of the same size as your column vector T, but all the diagonal values are equals to 1. The reason we introduce this is so that it becomes a system matrix equation. Okay, you have a matrix times a column vector, because this times this will just give you the column vector. All right, and what is L? L, as I have said, it is the Laplacian matrix, and it contains all the coefficients in front of your central difference operator. Okay, now this equation is written in a very general way. It is written based on this central Kronecker-Nicholson scheme. When you apply your equation into the grid points as what we have done over here, you guys know that when you apply it, every time you apply it, if there's a boundary condition, you move it to the right-hand side. When there's a boundary condition, you move it to the right-hand side. So if you account for the step where you have moved all the boundary conditions to the right-hand side, you can then rewrite this as matrix I times T at n plus 1 minus d delta T over 2. This will still be your Laplacian term. And on the right-hand side, you have again the same thing. But here we are going to say that we will have two terms and we account for all the boundary condition value. So whenever you collocate it at a point and you have a point that belongs to the boundary condition, you're going to move it to this right-hand side. And all this right-hand side will correspond to this. Okay, so how is this easier and less tedious than the previous step? You need to try to set it up to see the benefit of it. Okay, so first of all, when you write it in this term over here, you can see that the only thing that you actually need to set up is to set up the Laplacian matrix. Okay, because identity matrix is an identity matrix, this is a column vector of all the temperature that you want to solve for. This will just be the boundary condition value. Okay, So the only thing that you have to set up in your matrix is the Laplacian matrix. Okay. So how do you set up the Laplacian matrix? You need to first of all write the column vector of all the unknowns, and then you're going to fill each row corresponding to the finite difference stencil. To set up the Laplacian, we need to write the first of all write the column vector of unknowns. So going back to the example that we have before, we have 9 unknowns. Okay, so we know that from the system matrix here, it is always a Laplacian matrix multiplied by a column vector of unknown value. Okay, we set tjk to be a column vector of t, but because in this equation here, we have accounted for the boundary condition, which we have moved to the right-hand side, your column vector should contain only the unknown temperature, not all the grid points. Okay, meaning that for the problem that we have before this, we have 9 unknown values. So those 9 unknown values are basically T11, T21, T31, all the way to T33. So these are your column vector of 9 unknown values. Okay, and this column vector should be multiplied to a matrix. And this matrix should be a 9 by 9 matrix so that it can be multiplied to a 9 by 1 column vector. Okay, so the objective now is to fill in this blank space here with the 9 by 9 coefficient from your Laplacian matrix. Okay, so what do? We need to again apply the stencil as what we have done before. Okay, so the first row, okay, so this is the first row, and you can see there will be 9 spaces for you to fill in the 9 coefficient. The first row will always correspond to the first equation, and the first equation is the first collocation. So if you recall from what we have before, the first collocation is when j equals to 1 and k equals to 1. Okay, so for j1 and k1, all you have to do is draw the stencil that we have. Okay, so you have 1, 1, 2, 1, 0, 1. Okay, and then you have 1, 0, and 1, 2. Why do I put brackets? Okay, so this is the stencil when you apply it at j equals to 1 and k equals to 1. Okay, now what I haven't mentioned is actually what the Laplacian is. The Laplacian, as I have said, are the coefficients in front of your unknown temperature within your spatial derivative. So in this case, in your Laplacian, you know that you have j plus 1, k minus 2tjk plus j minus 1 and k. Okay, and then you also have your tjk plus 1, jk, oops. And then you have your jk minus 1, and then you have your delta y squared. Okay, so you can see you have jk from these 2 terms. So what you can say is for your tjk, for your jk terms, the coefficient in front of it will be negative 2, 1 over delta x squared plus 1 over delta y squared, correct? Okay, the coefficients in front of your jk term will be minus 2 times 1 over delta x squared plus 1 over delta y squared. And then in front of your, okay, maybe I'll write it this way, for your jk. Okay, for your j plus 1k, okay, for j plus 1k and j minus 1k, this will always be 1 over delta x squared. For j and k plus 1 and j k minus 1, the coefficients in front will always be 1 over delta y squared. This is from the central difference scheme. So right now, if you look at your stencil right here, whatever coefficients that you fill in this first row will actually be multiplied to the column vector that we have. That's your matrix multiplication operator. Okay, so the first coefficient should be multiplied to T11. The second coefficient should be multiplied to T21. So whatever you fill in here will just be based on your stencil. Okay, so to make things simple, let me call this alpha. Okay, so that I don't have to write this entire thing. So you can see when you apply your your stencil to J1 and K1, the J1 and K1 is your JK. Okay, so your JK has a coefficient of alpha in front of it, so you put in your alpha here. The next point is your T21. So T21 is your J plus 1, so this becomes 1 over delta x squared. Okay. The next one is a T31. So T31 is actually beyond your stencil. This is your 31. If it is beyond your stencil, it is not in your equation, so you put a 0. Okay. Next one is your T12. So T12 is 1 point up, which is your K plus 1. So if it's K plus 1, the coefficient is 1 over delta y squared. The next will be T22. T22 is actually here, again, beyond your stencil. So it will be 0. And if you follow the rest, you'll find that these are all 0. Okay, so all you have to do is set up your Laplacian based on the system matrix of equation that we have written here. So this does not set up completely because you are only solving it for one row. Yes, Kelvin.
Sir, so when you set up the Laplacians, you don't have to deal with the point at T01 or T10, right?
No, those will be the boundary condition vector that you will set it up separately.
Oh, okay.
Yeah, because when you set up your Laplacian, it is always referring to, if you recall what I wrote earlier, your Laplacian multiplied by a column vector. So your column vector, as I have said, does not include the values at the boundary anymore. They are all the values of unknown. So you can see T01, T10, all the points at the boundary are not in your column vector. So they are not influencing how you set it up. So, okay, so this is for the first row. For the second row, it will be the same. Okay, so this is your first row. For the second row, the stencil will now be at J2 and K1. So again, this is your 2, 1, 3, 1. This will be your 1, 1. So right now, this will be 2, 2, and 2, 0. Okay, so again, we do deal with it the same way. The first coefficient is multiplied to T11. But right now, T11 is not your middle point. Your center point is now T21. Okay, so what is T11 with respect to this collocation? With respect to this stencil, what is T11? T11 is J minus 1K. All right, so if it is J minus 1K, this will be 1 over delta X squared. Okay, the next coefficient is multiplied to T21. So T21 we know is the center point. If it is a center point, it's alpha. T31 is the next point. It's a J plus 1. You know, it's 1 over delta X squared. So from here, you can actually set it up very easily. Okay, you can see for T12, it is not in our stencil, so it was 0. For T22, it will be K plus 1, so it will be 1 over delta Y squared. And you find that the rest are going to be 0. Okay, so you can effectively do the same thing for J3K1. You can fill in your your row for the third row, and you can repeat this for all the remaining stencil. And finally, you should end up with a system matrix that is 9 by 9 to correspond to the column vector of 9 unknown values. Okay, boundary condition will be set up in the same way. I'm just trying to rush this a bit because of the time. When you set up your boundary condition is not a matrix, it is just a column vector. So for example, when you set your point to J1 and K1, again, it's a matter of just looking at the stencil. Your middle point will always be J and K. So this will be 2, 1, this will be 0, 1, this will be 1, 0, and this will be 1, 2. So you know that everything with a 0 will be your boundary condition. So here, if they are all 0, if you add them up, then it becomes 0 over here. Okay, and you can see that the only time they are not 0 is when they are at the on top, okay, at the horizontal top boundary. So what I want to mention is to answer the question, I believe it was from Kelvin. Where is it? What do you do with these 2 points? You can see because of the way the stencil is set up, it doesn't matter what this point is because your stencil will never hit that point. Okay, when you apply a stencil, when you apply at this point, this will be the 5 points of interest. When you apply at this point, this will be the 5 point of interest. So whether this point should take a value of 10 or whether this point should take a value of 0, it doesn't matter. Although realistically, physically, it has to have a temperature at that point. Okay, but and you cannot have one single point with 2 temperature. You cannot have one single point in space with 10 degrees Celsius and 0 degrees Celsius. So we are not talking about something that is happening realistically. We are talking about what we would prescribe in a model. So from a modeling point of view, this point doesn't really matter.